The structured questions then, question 1. We're looking at ultrasound making an image of an unborn baby, and the question is how, for 2 marks. Well, it's about reflection from a boundary between 2 media. So it's about the reflection at that boundary between 2 media of different density. You know that any wave, when it goes from one material into another of different density, you will get some reflection from the boundary. So if we had air and glass, your ray of light comes in, it will refract. That's supposed to be a change of direction, sorry about that. It will refract, but you will also get reflection. That happens with any wave going from one material into another, a different density. So, reflection for 1 mark from that boundary, and the time between emitting the ray and the return of the reflection, that's used to make your image. So 2 marks. The reflection from the boundary between the 2 media, or you might name them, you might say, water, fat, muscle, bone. That's how it works. And it is the time between the emission and the receipt of the reflection that allows the machine to work out where the various bits are. So that's that. Another use, well, there's lots of these. Sonar, cleaning delicate machine parts, mixing paint. You can use ultrasound to do that. Welding plastic, motion sensors, and these are the ones that I have told you about particularly, and possibly that one. So that's question 1, 1 and 2. Question 2 then. How many waves are produced by the loudspeaker in 0.001 seconds? Well, let's have a look. There's 1. There's 2. There's 3. There's a little bit more, but our 0.001 starts here. So I included that bit and shouldn't have. So it's 1, 2, 3. 3 waves. How many waves are produced by the loudspeaker every second? Well, you've got 3 waves in 0.001 seconds. So you're going to have 30,000 waves. Produced. There should be another 0 on there, sorry. In 1 second. A person with normal hearing cannot hear the sound produced by the loudspeaker. Why? Well, the frequency, number of waves per second, is greater than 20 kilohertz, which is the maximum hearing for humans. Part B then. The diagram shows how a very high frequency sound wave can be used to check for internal cracks in a large steel bolt. The oscilloscope trace shows that the bolt does have an internal crack. So, what happens to produce the pulses A and B? A is the transmitted pulse, so it travels through the steel bolt. It hits a change of density at A, and then it hits another change of density at B. So you would expect a change of density down here, wouldn't you? Where it goes from steel into air. So that's B. A then must be the crack. So A is reflection at the crack. B is reflection at the end of the bolt. Part 2. Use the information in the diagram and the equation in the box to calculate the distance from the head of the bolt to the internal crack. Right. Well, we have 1, 2, 3, 4, 5 squares, and each of those squares represents that much time. So we have 5 times, and let's have a look. We have 1, 2, 3, 4, 5 zeros. 0.12, oh hang on. 0.1234 zeros is the time, and that is the time for the wave to go into and back from the crack. So the velocity, distance divided by time. So the distance then would be the velocity times the time. Our velocity, we are told, is 6,000 meters per second times 5 times 0.1234 zeros. But of course that's twice the distance. That is the distance from here to the crack and back. You've got to divide that by 2. And if you do the numbers, you'll get 0.075. So the key thing here is to realize that each of these squares is that much time. You've got 5 squares between here and here, but that is the time it takes for the pulse to go from here to the crack and back. So we're remembering this factor of 2. This is working out twice the distance we need, divided by 2, 0.075. If you got 0.15, which is twice that, you lose a mark.